So I just want to kind of take you through a kind of more complicated example where doing this by hand is really not a good idea. So using a computer to help you with various steps. But also this will go through just the general steps we need anyways. So we've got a initial value problem. It's a second order equation. Y double prime plus 3y prime plus 2y is equal to x times sine of 2x. And we got our initial conditions, y of 0 equals 0, and y prime of 0 equals 1. This is just, in Maple, this is just text. It doesn't have anything to do with, it's just kind of letting us know what problem we're working on. Well, let's think about the general strategy of these problems. The first thing we have to do is solve the homogeneous equation, which is the solution to setting this stuff equal to 0 and solving. So how do we do that? We have to find the roots of the characteristic equation. So we can, in Maple, we can just type solve. We type the equation we want, which is going to be r squared plus 3 times r plus 2 equals 0. Solving, r is the variable. So if I do that and hit enter, it'll give me the answers. But what we can actually do is we can assign that. We can assign those and call this r. When you set things equal in Maple, you just use a colon equals, and it defines this output, and it gives it the label r. So what that means is r is actually a vector of two numbers. The first number is -1, the second is -2. To see this, I can just illustrate. If I put r1, bracket 1, it tells me the first number, which is the -1. If I were to put 2, it would give me the second number. So that just gives us a way of labeling things generally. So since we know those are there, we know what our homogeneous solution is. Let's call it YH. We need to put a subscript here. Let's just call it YH. We're going to define it as a function. So we define a function in Maple. You just type x, the input variable, and then an arrow. And then you define your function. So what is our general solution? Since we have two real roots, it's going to be some constant C1. I'm going to use capital C 1. That's how we indicate to Maple that you want a subscript. So C1, just like R1 and R2 are different numbers. C1 times the exponential of what? Well, R1 times x, which happens to be a -1x, and then plus the second term, capital C2, times the exponential R2 times x. So it just gives us a visualization of, yes, that's our homogeneous solution. We know what R1 and R2 are. We don't know what C1 and C2 are. So now what do? We move on to our particular solution, y sub p. And remember, what do we have here? We have a product of two functions. We have x and a sine of 2x. So as we saw in the kind of complicated example at the end of the notes, in this case, it's a linear function times a trig function. So we're really going to have four terms. We have an x and a sine term, a constant times a sine term, an x times a cosine term, and a constant times a cosine term. Those would be the four basic linearly independent functions we're going to need to construct y sub p, because if y sub p has that form and we plug it into our linear differential operator here on the left, it will still be a linear combination of those functions. All right, so we're going to define yp. So we'll just use lowercase letters here. So I'm going to do it in x. Yp is going to equal the function that takes x to. I'm going to do it kind of like in the notes. I'm going to have a times x plus b, that's our first linear term, times our sine of 2 times x. And then we're going to do a second term here with a linear term. We'll use c times x plus d. I'm using lowercase letters because some of the uppercase letters are restricted in Maple, and since I'm using a lowercase c here, that's why I used capital C's for the c1 and c2. And we have to multiply that by the cosine of 2 times x. So that's our general guess. That's the format that we would need to have. And the undetermined coefficients are just a, b, c, and d. So that's stored in yp of x. So what's the next thing we have to do? We have to determine those coefficients. So we have to basically evaluate what we get when we plug yp into our linear differential operator. So we have to compute the second derivative of yp. This is just done with diff. So derivative. There's a couple ways you can do this. If you want two derivatives, you just put x, that would be the first derivative, and if I put another one, that would be the second derivative. Or you can use a command like x $, and then the number of derivatives you want. Either one works. That'll be the second derivative. And what do we have to do? We have to add to that 3 times the first derivative of yp of x. And then to that we have to add 2 times yp of x. Now, if I compute this out, let's see what it is. It's going to do all the work for us, but it gives us this horrible mess of stuff. And a lot of the like terms haven't been combined yet. So again, what do we need to combine our like terms as? We need to combine them as x's and sines, constants and sines, x's and cosines, x's and constants and cosines. So there's not the greatest way of doing this, but it works. There's a function in Maple called collect. It just basically means combining like terms. We're going to put all of this inside of collect, but we have to tell it kind of in order of what we want to collect. So we want to collect x terms, sine terms, and cosine terms all together. So it's kind of done that for us. Let's see what it actually did if we look closely. This first term here, we've got 2 things here, all inside of parentheses, and then times x. So if I distribute this x, this first term is really the x sine 2x term, and this is the x cosine 2x term. And then the next term here is just our sine 2x term, and then our last one is just our cosine 2x term. So we have our 4 terms. So we just need to solve a system of equations. So in order to do that, again, you can use solve. And we just have to type in our equations. Well, what are our equations? So remember this first set of coefficients here, that corresponds to our x sine 2x term. So I'm going to copy that and paste it. Uh-oh, did something crazy here. Let me undo that. So I'll try that again. We're copying, this is our coefficient of our x sine 2x term. Paste it there, and I want that to be equal to what? Well, our phi of x is 1 x sine 2x. So let's set that equal to 1. And the next equation, our x cosine 2x coefficient is here, so I'm going to copy that, paste it next, and since our phi of x doesn't have such a term, that's going to be equal to 0. And then our third term, we have this coefficient involving all 4 of our undetermined coefficients. That's our sine 2x term. Again, phi doesn't have a sine 2x term, it only has an x sine 2x term. So this is equal to 0. And then our last equation is, oops, something's wrong here. Our last coefficient is this, and this is for the cosine 2x term. And there's no cosine 2x term in phi of x, so then again that's equal to 0. So we have our, when we close our bracket here, and we have our 4 equations, and we just have to tell Maple what the unknowns are in another list. Now if I hit enter, it's going to solve this system of equations for me. And it tells me what those values are. But the problem is it hasn't actually put those values and stored them as A, B, C, and D. So there's an easy way around this. After you have this solve, you just put what's called a sign. And then another parenthesis there. And now it will actually solve the system and assign those values to A, B, C, and D, so we actually have our exact value of yp of x. And we can check and see what happens if I type yp of x. It'll probably still say, oh, there we go, it's put the numbers in. So you see we have the exact, now we have the exact form of yp of x. I don't really need that. We don't really need that. That was just confirmation. So what's next? We have our general form of our homogeneous solution with the constants c1 and c2, and we have our particular solution, yp of x. So we need to construct our general solution, y. So y is equal to the function that takes x to yh of x plus yp of x. And again, notice it doesn't actually, it just tells you what it did. If I want to actually see what y of x is, I can just type in y of x. And now we can see here's the homogeneous part, and then here's yp, the particular solution. Again, we don't need this. So at this point we have y of x, the general solution. So what do we have to do? We have to use the initial conditions. Well, the first initial condition is y of 0 equals 0. And the second initial condition is y prime of 0 equals 0. So again, we don't really need to see this right now. So what do we really have to do? We have to solve a system of equations. Again, the first one is y of 0 equals 0. The second one is the derivative of y at 0 is equal to 1. Now, in order to do this, we have to differentiate y of x and x. But then we have to evaluate it. So we have to evaluate that derivative at x equals 0. And we know that that has to be equal to 1. So there's our two equations, y of 0 equals 0 and y prime of 0 equals 1. And we have to tell it what the unknowns are. Well, the unknowns are capital C1 and capital C2. And there you go. But again, it didn't actually assign those, so we can use the assign around this solution. And it will actually put those values into C1 and C2. Now if I type y of x, I can actually see the exact solution to our problem. So again, the point of this is I want you to understand the process. You solve a homogeneous equation, it gives you a general solution. It gives you some unknown constants C1 and C2. To find the particular solution, we have to create the right guess, plug it into the equation, and then set up a system of equations to determine those undetermined coefficients. And then we just have to add those two things together to create our general solution, y, and then we use the initial conditions to set up a system of equations which will allow us to solve for C1 and C2 and C3, C4, so on, depending on how many terms your y sub h actually has. Now in the end, you can always check to make sure everything's working. So let's just confirm that we have our solution. Well, we know that the second derivative of y of x plus 3 times the derivative y of x, first derivative, plus 2 times y of x. Whatever that should be, it should be x times sine 2x. So let's hit enter and see what that is. Oh, it gives us a whole bunch of stuff. Well, it didn't simplify it. In this case, we can just do a quick simplify here. It's another way. It doesn't always group things the way you want it, but in general, these kinds of things it will. And there it is, x times the sine of 2x. So our y of x does satisfy the differential equation. If I plug in y of 0, do I get 0? Yes. And if I evaluate the derivative of y of x at x equals 0, I should get 1. So we have our solution, our y of x, right here.